Hello, my name is Caio Vitorino, and in this video I'm gonna present you the inverse kinematics of the UR5 robot from Universal Robots. So first of all, I'm gonna use this simulator that's called Isaac Sim from nvidia, and I made a simple user interface using Theta for you to control the robot, like sending some joint angles to ROS2 or sending the position and orientation of the end effector with respect to the base. So first of all, I'd like to show you how this works. We're gonna calculate the position and orientation of the ROS3 link with respect to the base link inertia. So it's very important to understand this concept because if you accidentally use the base link frame instead, you will get the wrong position or orientation of the end effector. So for example, if you want to directly send the joint positions in order to study the inverse kinematics, you can uncheck nvkin and you just put the joint angles and then send to the robot. And if you want to use the inverse kinematics instead, you write the x, y, and z values, and then the rotation about x, y, and z with respect to the base link inertia. So I'm gonna do it now. If you notice here, by visualizing the frames, the ROS3 link is rotated 90 degrees in the y direction with respect to the base link inertia. So I also implemented this interactive marker, so you can easily change the position and orientation of the end effector. It's actually working with a ROS2 action server that receives the joint angle and interpolate the trajectory using the initial and final position using kinetic trajectory planning. So be aware, pay attention to this detail here. The end effector is pointing to the z direction of the marker. So if we put the marker in this orientation, the robot will move and reach the position that you configured. So be careful to not set a I don't know, crazy orientation and you get an error or maybe hit the table. Yeah, let's go to the presentation. I'm Caio Vitorino. I'm a PhD candidate in electrical engineering in the field of robotics and artificial intelligence. And if you want to contact me, please send me a message on LinkedIn or just leave a comment in this video comment section. And I also have a master's in mechatronics engineering. So if you want to message me to discuss about robotics, artificial intelligence, and general topics, I'll be happy to discuss with you. So there are some knowledge that are required to fully understand this video. I'm not gonna discuss ROS2, but I'm gonna leave the link to the GitHub repository for you to access the code that I'm using to run this simulation. And if you want to use the code, you have to understand how ROS2 works. And also you need to install Isaac Sim from nvidia and understand some basic concepts about rotation matrices and homogeneous transformation matrices. Also the inverse kinematics of a planar robot and some basic math concepts that I'm gonna discuss in the next few slides. So this video is specially made for my colleagues at the robotics laboratory at the Federal University of Bahia. So if you want to visit their YouTube channel, go to this link here. And if you want to access the code that I'm using, here is the link. I will put the link also in the video description. So feel free to collaborate and send pull requests. I'll be happy to work with you. First of all, you must pay attention to the robot workspace. Like I said before, we are calculating the pose of the end effector. When I say pose, it's position plus orientation. So we are calculating the pose of the end effector with respect to the base link inertia. So you must be aware of this link here, because the coordinates that you set in the algorithm will deeply impact of course, the position of the end effector, and you may hit some object or the table. It's dangerous. So yeah. Also, the inverse kinematics that I'm gonna present to you is based on this paper here. Actually, it's not a paper, it's a PDF that's free, available on the internet. It was published by Ryan and Noah. And also, but actually, the inverse kinematics that's in this PDF here does not work with the URDF that's provided by Universal Robots. So I just had to make some minor modifications to some frames and some math to fully work with the URDF that Universal Robots provides. So these are the parameters that I'm using. For example, we have some translation in the z direction from the base link inertia to the shoulder link, and shoulder link rotate by theta 1 with respect to the base link inertia, and that's how you interpret this table. And also it's important to pay attention to the link number, because it will be part of the symbols to represent the homogeneous transformation matrices. So first of all, if you go from the base link inertia to the shoulder link, you first translate in the z direction by z0. And when I say z0, it's translation z by this index number here. So this is this number here that I'm showing you with the mouse pointer. So after you translate, you rotate by theta 1 in the z direction. I just put some code here. This code is available in the GitHub repository. So if you want to follow along with the code, it will help you understand what's happening here. Also, from shoulder link to the upper arm link, we have a rotation by 90 degrees by x in the x direction, and upper arm link rotates by theta 2 in the z direction also. We have also a from upper arm link to forearm link, we have a translation in the z direction by x2. This is this number here. And then forearm link rotates by theta 3 in the z direction. So in the z upper arm link direction. Actually, you will notice that all the rotations occur locally. So the frame rotates in its own origin, not with respect to the previous link, but just download the code and play with the tool, and you start noticing some behaviors like this. Also, from Forearm Link to the Forearm Link X, actually I created this link. It doesn't exist in the URDF file, but I created this to facilitate the understanding of the math that I'm going to present you in the next few slides. From Forearm Link X to ROS1 link, we have a translation by Z4 in the Z direction, of the frame Forearm Link X. And also ROS1 link rotates by theta 4 in the Z direction. Okay. From ROS1 link to ROS2 link, we have a rotation about X by 90 degrees. Then you translate by Z5 in the Z direction of ROS1 link, and then you rotate by theta 5 in the Z direction. So that's the relationship between ROS2 link, it's this number here, number 6, to ROS1 link, or number 5. And finally, from ROS2 link to ROS3 link, you have a rotation by minus 90 degrees in the X direction, then a translation in the Z direction to the ROS3 link, and then a rotation around Z by theta 6. So here's the math, and here is the corresponding code. Finally, let's go to the inverse kinematics equations. Like I said before, if you are working in the laboratory of robotics at Federal University of Bahia, please, and you are trying to pick an object on the table, choose the solution 5, because it will be shoulder right. It's the home position that we configured for the robot in the laboratory. Also elbow up and wrist up, like this position here. Okay, so it's the best solution to work with grasping algorithms and things like that. Let's start with theta 1. First of all, you know the transformation between frame ROS3 link to the base link inertia, because that's exactly the desired position and orientation. So in order to find theta 1, you will have to find the position of the ROS2 link, because we're gonna calculate some angles to find theta 1. So if you perform this displacement in the minus Z direction by D6, that is this number here, you would end up finding the position of ROS2 link with respect to the base link inertia. So yeah, in order to find the distance in the XY plane of the frame base link inertia to the ROS2 link, the origin of the ROS2 link in the XY plane, you just calculate like this. You have the component of the Y component of the point and X component. It's easy to calculate, and then you find the beta angle. Just notice that the end effector is in the minus Y direction with respect to the base link inertia, and in this case beta is negative. Also, you have this gamma angle that is fixed, because it's the relationship between the arc cosine of the adjacent side by the hypotenuse that you have. That is the already actually the hypotenuse that's already calculated before in the step before, and then to find theta 1 you just sum 90 degrees to beta and to gamma. So you have two solutions in this case, shoulder right and shoulder left. And to find theta 5, first of all, you have to find the relationship between wrist 3 link to the upper arm link. It's not difficult because you already have theta 1. So if you have theta 1, you are capable of calculating the orientation and position of the upper arm link, that's frame 2, with respect to the link 0, that's base link inertia. So in order to find the transformation between frame 7 and 2, you invert this matrix and then you multiply it by the desired desired transformation, position and orientation, and then you have this relationship, the position and orientation of this frame with respect to this one. So we have this component that's the position of frame wrist 3 link with respect to the upper arm link in the z direction, and we need to find some other correspondence of this distance using the parameters of this table. So notice that this distance is equal to z4 plus z6, but wrist 3 link rotates with respect to the wrist 2 link by theta 5. Actually, wrist 2 link rotates by theta 5, and then it changes the position of the wrist 3 link. So if you want to still find the distance between this line here to the upper arm link, you have to project the z6 into this direction using the cosine. So you have this relationship here showed in this equation, and then you find theta 5 by calculating the r cosine of this value. So it's important to keep the numerator less or equal to the denominator because of the domain of this function. So if you don't do this, you have a value error in the Python code. So theta 6, you just treat this problem as spherical transformations between the frames of the wrist. So for example, I just draw some frames here. The frame number 5 is the wrist 1 link, frame number 6 is the wrist 2 link, and frame number 7 is the wrist 3 link. To go from frame number 5 to 6, you have a rotation by 90 degrees in the x direction in this position, this rotation, and then you rotate around z by theta 5, and then you translate, you rotate back by minus 90 degrees in the x direction and rotates by z in the z direction by theta 6. If you multiply all these rotation matrices, you will get this rotation matrix. And you know that tangent is sine by cosine, so we need to get this relationship with the elements of this matrix. For example, if you take the this element here, the second row in the last column, and you multiply by -1, you will end up with sine of theta 5 times sine of theta 6. And if you divide by sine of theta 6, theta 5, you end up getting sine of theta 6 only. So the same applies to this element here, that if we take this element and divide by sine of theta 5, you end up getting cosine of theta 6. So actually what I mean by using this notation here is the projection of zeta, the z-axis of the frame 6 in the x direction of frame 4. This is exactly the first row, the last column of the rotation matrix. So, and to find theta 3, we treat this problem as a planar two revolute joints, and we use the plane that is created by the x and y direction of the upper arm link that's aligned with the x and y directions of the frame forearm link and forearm link x. So in order to do it, we have to find the transformation between frame 5, that's wrist 1 link, to the frame upper arm link. Why? Because we need to translate the position of this wrist 1 link in the -z direction to this plane that I mentioned before, that's created by the x-y direction of the previous frame. And we have, in this case, we have three frames that are aligned on a plane, the same plane. So by using the law of cosines, we can find this lambda angle, that is this angle that's formed by the elbow here, and we know that cosine of lambda is equal to cosine of theta 3. Why? Because of this. Just simple math. If you apply some algebraic relationships, you notice that cosine of lambda is equal to the cosine of theta 3. So we can easily find that theta 3 is plus minus r cosine of this value here, and it represents the elbow up and down configuration of the arm. So if you are working like I showed before in this case, just prefer to use elbow up configuration. That's solution 5 of the matrix of solutions. To find theta 2, we just have to calculate this gamma angle. That's the arctangent of the opposite side. That's the y component of the of this point, or the frame 4 with respect to the frame 1 over the y component of the x component of the frame 4 with respect to the frame 1, and also this beta angle, it is the opposite side, or x3 times sine of theta 3, or this component here, over the adjacent side, that is x2 plus x3 times cosine of x3, actually this direction here, times cosine of theta 3, or this projection here. And then we calculate theta 2. We notice that this is the negative angle, negative theta 2. If you want to play with the 2 that I showed in the beginning, you will have a more practical understanding why this angle is negative. And the theta 4 angle, that is the orientation, or the orientation of the ROS1 link with respect to the forearm link. So we know that this orientation is just a rotation about the z-axis. So we can calculate it by using the arctangent of this matrix. So we have sine in the first argument and cosine of theta 4 in the second argument. So, and also, how do we get this rotation matrix? It is the relationship between the frame 4 and the transformation matrix between frame 4 to frame 3. But since we don't have this direct transformation, we can go from ROS1 link to the arm link, then to forearm link, and then to forearm link X, using this transformation relationship. So this video is not about transformation matrix, but yeah, it's just to give you a brief overview about how this works in theory and also in practice. Please check out the GitHub repository to visualize how this works. And keep going. How can you improve the inverse kinematics presented? Please notice that we have some error associated with the equations that are shown here, and try to minimize these errors, or maybe implement a new technique to calculate the inverse kinematics by hand, and try to add some sensors to the robot, like RGBD camera, and visualize the data in RVs to help you grasping objects. And also, we can't yet control the robotic gripper in simulation, but it should be pretty easy. It just works in the same way as I did for the joints. So try to implement it in ROS2 and connect to the Isaac scene simulation. So that's it for today. Thank you for your attention, and sorry about anything that I did wrong. Feel free to comment here in the video, and I will be happy to answer your questions, and feel free to contact me on LinkedIn as well. So bye bye.